Welcome back to ECE 441A, 541A. We are in our next to the last week of class. We only have 5 times remaining together, 3 this week and 2 next week, and then we have our final exam a couple of weeks from tomorrow, and that will be on the 11th of December from 10:30 to 12:30. That is on a Tuesday, so make note of that. Homework number 8 is due on an odd day, I guess, just to get you used to that Tuesday shift. That's now due on Thursday at the normal time. That's homework number 8, and that's dealing with Bode plots, and in particular sketching and system identification. Lab number 3 is due on the last day of class, as is the project. If you're in 541, you'll have both deliverables 2 and 3 due on that day. Today what I want to do is get into controller design using Bode plots, and we will begin with a controller that we didn't spend a lot of time dealing with when we were dealing with it in the root locus based design, but you could think of this as like a PI controller without the derivative. This is a phase lag controller. PI though means you're forcing your pole to be right at the origin. Phase lag in general doesn't demand that or require that. And we'll talk about when we might want to use a phase lag controller, the concept, and then since it's in this cooking season, I'll give you a recipe. What's the recipe for producing a phase lag controller using Bode plot techniques? We'll go through an example, and then we'll get into the next controller design using Bode plots, and that's the phase lead controller. That will probably have to wait until the next time we are together. But here's the idea in the S-plane. In the S-plane, a phase lag controller happens very close to the origin, if not right at the origin. You have a pole now to the right of a 0 in a phase lag controller. The phase lead had just the opposite. The 0 was closer to the imaginary axis, and they could be a considerable distance away from the imaginary axis. With a phase lag controller, both your pole and 0 are close to the origin, and really what we're playing with is this ratio, or the distance between the pole and the 0. How do they now differ in terms of their location? But they're basically very close to one another. That's the picture in the complex S-plane. In terms of concept, now we are actually saying go ahead and allow us to slow down the system. We're not having to push the bandwidth higher. We can actually make the bandwidth smaller, which means that we can reduce the gain crossover frequency omega sub g. And typically what we're doing with a phase lag controller is we're focusing on steady state accuracy. We're trying to achieve particular performance in terms of steady state behavior. How is this system tracking a constant? How is it tracking a ramp? What are our error conditions? And so you might be given a steady state error specification. From that you can find your position gain constant or your velocity gain constant, your k sub p or your k sub v. That then translates into the k of your system. So let's look at what that means relative to a, let's say, a typical Bode plot picture in the frequency domain. Here's the frequency response. The top curve, and these are stacked on top of each other. The top curve is a hypothetical magnitude plot as a function of log of omega. Remember, we went to the bookstore and bought this semi-log paper, or we actually know how to do that on gridded paper because of the relationship of these numbers with log of omega. But here is our magnitude, and 0 dB is indicated. And right below that plot is the plot of the phase curve. And I've tried to identify a couple of locations on this plot with this green vertical line, and it actually connects the two plots. And the reason I'm interested in those two frequencies, remind me, what's the frequency called up in the top figure? Or what do we label that? Do you remember? Was the break too long? That's our gain curve, so that's now, if you don't remember anything else, it's an omega, it's a frequency, and it's our gain curve, so it's omega sub g. It's our gain crossover frequency. It's where the magnitude crosses 0 dB, or in absolute sense, it's when g has a magnitude of 1. In dB, that's 0. But this particular point, frequency, is omega sub g. And that then should remind us what we call this, or how we label this frequency. That's the phase crossover frequency, and we call that omega sub p. Relative to those two frequencies, can you tell me anything about the stability or the stability margins with these two frequencies identified? Is this system stable? Or another way of asking that would be, are both of my stability margins positive? Do I have a positive gain margin, and do I have a positive phase margin? Where do I find those in this particular plot? Where do I find my gain margin? Or what does that really mean? That means how much can I crank up the gain before I reach this critical value of magnitude of 1 at an angle of minus 180. If I adjust the gain in this system, does that modify the phase curve? If I change the gain, if I want to change the gain in this system on G, if I increase that, let's say it was a nominally 2, and I say, oh, let's make it 5. Do I now have to resketch the phase? How does that gain influence the angle or the phase information? Does it? No. So the gain, I'm simply going to shift that up or down with a gain increase. So now I can increase the gain or decrease the gain to satisfy my steady state air specification. And let's assume I've done that now, and this particular sketch now is a consequence of me adjusting the gain in my system to achieve steady state accuracy, which is probably meaning that I was focusing on what's happening here at low frequencies in terms of my gain. But now what I want to do is say, if that's the case, how much can I increase the gain in this situation? Is my magnitude curve below 0 dB when the phase crosses over minus 180? Yes, so that means I can actually shift the phase curve up. There is a gain margin in this case, and it's found right here. It's this distance in dB. This is now my gain margin, GM. And I might even call that GM sub U for the uncompensated gain margin. Uncompensated meaning I haven't introduced any poles or zeros yet from my controller. I have adjusted the gain. Now that I've identified where the gain margin is, what's my phase margin? That's how much I can take away from the phase, reduce it before it crosses minus 180 when the gain curve is at 1 or 0 dB. This then is my uncompensated phase margin. Maybe now somebody says, oh, I'm not happy with that phase margin. Maybe it's 20 degrees and they're not happy with it. They want to increase it. And the phase lag controller says, oh, but I'm okay slowing the system down. Slowing the system down really means that I can make that omega sub g occur farther to the left or at a lower frequency than it currently is appearing. So slowing the system down, or speeding it up, in fact, speeding up the system says you want to make the bandwidth, the crossover frequency, higher. You want to speed up your system, so you're pushing that omega sub g to the right. Slowing it down says, oh, we can make that omega sub g smaller. And what happens if I now make that omega sub g smaller? Well, that now allows my phase margin to be increased. Do you see that if I now did the following, suppose that I said, oh, if I introduce a pole back here, and then I introduce a 0, do you see that I've now done that to my gain curve? This is now where I've introduced a 0. And I've now modified my gain crossover. I will call this now, maybe just to be a little bit more of a challenge, omega sub c prime. And this is now my compensated phase margin. And what we want to do is figure out, how do we know where to locate the pole, where to locate the 0 in order to make this happen. And if I actually do adjust the pole and the 0, or introduce a pole and a 0, does that modify my phase curve? If I put in another pole and 0 factor, does that adjust the phase curve? Let me say I put it in time constant form, so I don't adjust the magnitude other than with the breaks in my magnitude response. But now the phase curve does get modified. And what happens to the phase? Well, it might do something like this, but hopefully we adjust this pole and 0 at a low enough frequency to where the phase contribution has basically stopped almost before we get to that new crossover frequency. But you can see that I've undershot with that blue highlight a little bit, and that's what's going to have us put in a safety margin when we go through the design. The fact that we may not have all of our phase adjustment made by the time we now get to omega sub c prime. So let's now write down in words what I've tried to be saying in pictures. Now that you maybe see it, let me write it down, and then you'll have something to maybe refresh your memory with, maybe not. But I guess you could always go back and play the video, but you've probably had enough turkey. You don't need any more sleep-inducing impact or influence now. Maybe some of you didn't have turkey, but maybe you had something. So let's now figure out or write down some of the strategies, the concepts that I've tried to communicate. How do we drop? And now I've actually given you the answer, but how do we drop the magnitude to allow this compensated. So now I'm putting in a G sub C with G to cross 0 dB at this new frequency that we agree would achieve our phase margin that we want, this omega sub C prime. And the way that we did that was to do what? We introduced a pole and then a 0. And that was in combination. So to do that, we wanted to actually introduce a pole 0 combination. And as we said, we wanted to make sure that where we located that pole and 0 was far enough or low enough in frequency to where the phase had pretty much done its course before it made it to omega sub C prime. We didn't want any more slop or adjustment of the phase. We kind of wanted to introduce the magnitude change low enough in frequency so that it didn't impact our phase curve much, because that's what we were hoping to achieve with omega sub C prime. So we don't want to change the phase curve near this new crossover frequency that we were labeling omega sub C prime. And the way that we're going to do that is really sort of in 2 steps. We're going to place, first we're going to determine what phase margin do we want, and once we find that, then we are going to place the controller 0. How far or how much lower in frequency do we need to adjust that in order for it to pretty much have run its course by omega sub C prime? What do we know about the contribution of phase from a particular linear 0 factor? Place the controller 0. How far to the left? Factor of 2, an octave. Factor of 4, 2 octaves. Factor of 8, 3 octaves. A decade, a factor of 10. How far below omega sub C prime do we want to place the controller 0 so that its phase has pretty much finished contributing angle? A decade, because we said what? These pole and 0 factors distribute their phase in our straight line approximation over a 2-decade expanse. And so if we now center that 0 a decade before omega sub C prime, its angle contribution is pretty much finished. So we're going to place the controller 0 a decade, a factor of 10 before omega sub C prime. That is, we're going to let Z sub C be omega sub C prime over 10. Now we have our 0 placed. We've already adjusted our gain K. The only thing left is to pick the controller. And how do we find the controller? If we now know where we're going to put the 0, how far back do we put the pole? What does that influence? The further we put the pole, or the lower in frequency we put the pole, the longer our gain curve is going to have to be attenuated or to drop. Meaning, the pole and 0 separation is what we're after, and we want to make that such that we get the attenuation needed. We want to now attenuate by what? This is actually, what color do I want to pick? We want to actually have that much attenuation at omega sub C prime. This is our attenuation that we need to accomplish with this separation of pole and zero. And that's really this second comment that I'm trying to make now. Now what we want to do is work with the controller pole and it is at a lower frequency than the zero, or it breaks sooner, and the pole causes our magnitude to go down. And this pole zero separation is actually influenced or actually determined by how much attenuation we need to have happen at this new gain crossover frequency omega sub c prime. How much do we need to lower the gain to make our gain curve cross at 0 dB at omega sub c prime? So the pole zero separation is determined by the attenuation needed. Enough already with the talk. Let's figure out the recipe. Let's figure out the strategy in a little bit more detail. Here is now how to design, and you're going to probably like this because this is more prescriptive than the root locus design. The root locus design is like, where do I start? What do I do? And if you look at the solutions to exam number 3, you'll see that there's many different ways of achieving the requested design. The disadvantage of asking such questions is it takes a long time to grade because you have 100 different correct answers for one problem, possibly, if everyone was thinking a little bit differently to create their solution. So here's how we will represent our transfer function for our phase lead controller. We're going to write it in time constant form, where the numerator factor will have our time constant tau, and then the denominator factor will differ from that by this difference between our pole and zero, a factor of alpha. Here is now our controller in time constant form. And if you don't like it written that way, you can sneak a zero and a pole in there by simply saying, oh, I'm going to have S over Z sub C, where my time constant tau is 1 over Z sub C, and now this is going to be 1 plus F S over P sub C. If we do that, hopefully it's clear that the zero is connected or related to the time constant that we've defined as 1 over tau, and our zero is now located at minus Z sub C. Our pole is likewise at S equal minus P sub C, which is now minus 1 over alpha tau, which is really just dividing the zero location by alpha. And alpha is the attenuation that we need. Or that's really the pole zero separation. Here's the recipe. To design a phase lag controller in a Bode plot situation. First is we want to determine the gain in our original plant necessary to achieve the steady state accuracy specification. So determine the gain necessary to achieve the specified or required steady state accuracy. Step 2 is we now need to sketch the Bode plot. Obviously we need something to begin with, and that's the sketch of the Bode plot. So now we plot, and this is a plot of what I will now refer to as the uncompensated. That means we haven't yet introduced any poles or zeros of our controller. So no poles or no zeros from the controller. That's what I'm referring to as uncompensated Bode plots. And we obviously want to sketch the magnitude using the gain that satisfies our steady state air spec that we determined in step 1. So that you should be able to do. Figure out what your steady state air spec, sketch your Bode plot. Now what we want to do is say determine the phase margin. And you know how to do that, or you will after you've now worked the homework number 8. So determine the phase margin for the sketch that you just created, which was for the uncompensated system. And that we are calling PM sub U. Now we get to ask some questions. If PM sub U is sufficient, then what do we do? We go to the kitchen and bring out a snack. We're finished. We can kick back. We can watch, listen, do what, maybe have a distraction for a few minutes. We're done with this problem. The phase margin is satisfied. So if phase margin uncompensated is sufficient, we really don't need to introduce any poles and zeros from a phase lag controller. No phase lag compensator or controller is needed. Maybe I should have been color coordinated. You can actually stop. Good luck with that happening on the final, right? So what happens if we can't? If the uncompensated phase margin is not sufficient, then we need to continue. So otherwise, we proceed to step 4. Step 4 says now if we don't have the necessary phase margin, now we look on our phase curve and we walk back to a lower frequency and say, where can I find the phase margin that I really want? So now we determine the frequency that we were now calling omega sub c prime. And omega sub c prime is determined, or is the desired, maybe I should say, is the desired gain crossover frequency. And we can find that omega sub c prime from the phase curve using what we will call Pm sub c. And omega sub c prime is the frequency where our compensated phase margin would be achieved if the gain curve actually crossed 0 dB at omega sub c prime. And now I haven't really said what Pm sub c is, so let me define that. The compensated phase margin, Pm sub c, is the desired phase margin we just have some two-letter acronyms plus SM. What? SM is safety margin. So safety margin is 5 or 10 degrees, depending on how the phase curve is sloping near that new gain crossover frequency. And you just pick a that number, 5 or 10, and add it on to your desired phase margin, and now you find what frequency that would occur at. Once we've found the new gain crossover frequency, omega sub c prime, in step 4, now we're in a position to actually find or locate the 0 of our compensator. Now place a 0 as we said, a decade below the desired crossover frequency. Omega sub c prime determined in step 4. Or we now have a formula for z sub c that's equal to 1 over tau if you need to know the time constant. But from step 4 we found omega sub c, and a decade below that is achieved by simply dividing that by 10. The next thing we need to do is figure out where to put the pole. So now we calculate the pole 0 separation using the amount of attenuation that is needed to cause the magnitude curve to cross the 0 dB line at omega sub c prime. So now we would come up to this plot and we would say how much attenuation is needed. If this value was actually at 30 dB, then we would need minus 30 dB of attenuation. That's what I'm saying for this step. I'm going to erase that, but you have it in memory. So now we have the formula minus 20 log of alpha. That's the separation between the pole and the 0. We set that equal to that attenuation needed value, which we said in our example was 30 dB. And in fact, this is a minus 30 dB. That needs to be a negative number. And once we have the right-hand side as, let's say, minus 30, and we have the left-hand side, our only unknown is alpha, we can solve that expression for alpha. Alpha now is simply divide both sides by minus 20 and take the anti-log of both sides. We have alpha. Alpha is now 10 raised to, because this was base 10 log, attenuation divided by minus 20. Once we have alpha, now we can find our pole, since alpha tells us how much lower the pole is than the 0. Step 7 now says calculate the compensator pole location using the value of alpha found in step 6. Or now P sub C is Z sub C over alpha. We had Z sub C from an earlier step. We just calculated alpha. There's now P sub C. This is now 1 over alpha tau, or omega sub C prime divided by 10 times alpha, where 10 alpha is in the denominator. Now we have our compensator. Now we have our controller. G sub C of S, our phase lag controller, is now 1 plus S over Z sub C over 1 plus S over P sub C. And on an exam, that's where you would finish. You would say, okay, I've done what I can during an exam. I don't have MATLAB. I don't have a way to quickly re-sketch this and check my work. But in the real world, you would actually verify that that meets your design specifications. So now you would draw the compensated Bode plot and that's now sketching, or really just introducing, G sub C of J omega onto your original G of omega Bode plot. And we now simply say is the new phase margin in this modified or compensated Bode plot, is the new phase margin large enough? If it is, again, we can pull out our red crayon and we can stop. If it isn't, now what do we do? If we didn't achieve the phase margin that we wanted, then we actually want to move lower in frequency with our omega sub C prime. So we decrease omega sub C prime. Or you could think of this really as increasing the safety margin in step 4. And then you actually have to go back and redo your design. Locate your 0, find your attenuation you need, find your pole, etc. So let's now see if we can use that recipe. Now we have all the ingredients. If you're cooking, what do? You always put everything out on the counter, everything's already measured, and then you just go at it, right? You just apply it. So let's now look at an example design for this phase lag controller. Suppose somebody gives you a plant, G of S, that's 10K over S, 0.1 S plus 1, 0.05 S plus 1. So we have a pole at minus 10, another pole at minus 20, and a pole at the origin. 3-pole system. And suppose that they now tell us our design specs. Are as follows. 1, they tell us that the steady state error due to a ramp, because we know with this type 1 system, if somebody puts in a constant, if our system is stable, then we're going to have 0 error due to constant inputs if our closed loop system is stable with this type 1 system. So we're really interested in non-zero errors due to a ramp. And suppose now that somebody says, oh, we want our accuracy to be such that the steady state error when we apply a ramp, a unit ramp, let's say, is less than or equal to 0.0333. And suppose that they say next that the phase margin is greater than or equal to 30 degrees. Those are the design specs that somebody now has suggested we achieve with the given system. So the very first thing we need to do is figure out, in this system, K was not yet fixed. We need to fix K before we can start drawing the Bode plot. Our steady state error is 1 over the velocity gain constant. And that was supposed to be less than this 0.0333 number. We can solve that for K sub V, and we can see that now the velocity gain constant needs to be bigger than 30. What's the velocity gain constant? Well, that's the limit as S goes to 0 of S G of S. And for that particular plant, it's 10K. And if we just say, oh, you know what, let's just barely meet our gain constant requirement. We set that equal to 30. Now we can see that K is equal to 3. So that the numerator now of our plant is 30, and the denominator, if we write it another way, is S over 10 plus 1 and S over 20 plus 1. So now what do we do? Well, now if you're sketching this by hand, you could sketch the Bode plot, but you could plug it into MATLAB. Not sure you're going to be able to. Can you see that MATLAB command window screen? I've defined now the transfer function G before class as a numerator, which is 30, and a denominator, which was a product of 2 polynomials, and I can form that product via the convolution function in MATLAB. So CONV basically does polynomial multiplication for you. And here I actually combined these two, and I had now S squared times 0.1 plus S plus 0. That's my first polynomial, and then the next one was that. And that's now what I've done in MATLAB in the denominator. I convolve those 2 polynomials, and I obtain a G that's 30 over that third order polynomial. Then I said, oh, sketch the Bode plot. I just said Bode G, and it produces this. And I should have put the grid on there. I apologize for that. But you know how you can cheat in MATLAB? All sorts of ways to cheat. But you can issue another command, which is margin. You can say margin G, which is what I did in a new figure window. And it actually gives me the gain margin and the phase margin. And if you look at this, you can see that, wow, you have a whopping gain margin, basically 0, and a phase margin of 0. And those are both occurring at the same frequency. So now this shift of omega sub g and omega sub p, or that difference between, doesn't even happen in this adjusted or uncompensated Bode plot. Now what do I do? What's my next step? You have this recipe memorized. You've been in the kitchen all break. You know how to memorize recipes, right? Take out a... Sorry, Julia Child isn't working just yet, but you could. Now, what do we do now? What's our approach? Do we have an acceptable phase margin? Is 0 acceptable? What did we want? We wanted 30, didn't we? And now I can't point to the screen very effectively. I should have cut and pasted this into OneNote. I'll do that maybe after the fact. But now we need to find an omega sub c prime, don't we? We need to figure out where is a reasonable gain crossover frequency to give us the phase margin that we want. Do we want, now how do I point at a screen that I have 8 screens to point at? Which one is available? I better not jump up on too many desks. What's the phase margin that we want? 30, but we need to introduce a safety margin, right? So let's say we introduce a 10-degree safety margin. So now we're looking to achieve a phase margin of 40 degrees. What's that mean? Well, now we look and see if we can find minus 140 on our phase curve, and where does that happen in frequency? It definitely doesn't happen at 2, does it? That's about where we're crossing. Oh, actually, we're at 14.1, so we're a little bit beyond 10 where we have our current omega sub g. Now we need to slide it back and try to get, I would say maybe even, let's just read across at minus 135. That would be a 45-degree phase margin. And where does that happen? Well, that might be a little bit easier to find. That looks like it's at 2, 3, 4, 5, maybe 6 in terms of frequency. Oh, what the heck. Let's just say that now we let omega sub c prime be 6. Does everybody see where that came from? We slide back until we try to get a phase margin value that we would like with the safety margin factored in. What have we now accomplished? What is z sub c? Do we have that? Yes, that's just divide 6 by 10. Now we need to go back to this curve and say, okay, if we're at 6, how much attenuation do we need to bring our magnitude curve down to 0 dB? So if we go back to 6, 2, 3, we're eyeballing this. Is that about 15 dB that we need to bring that, shift that magnitude curve down by? Let's just say that's the case. So now we say attenuation needed that allows us now to solve for alpha. Alpha is now 10 minus 15 over minus 20, or 10 to the 3/4, which ends up being 5.6. And now we have P sub c. P sub c is z sub c divided by 5.6, or that's now 0.107. So that now G sub c is 1 plus s over 0.6 and 1 plus s over, let's just make it smaller than 0.107. Let's make it 0.1. So I did that in MATLAB. If you see G sub c, that's what I've done here for G sub c. I combined G sub c of G, and then I did another margin command, and I ended up with this. And I did the margin, and what's my phase margin? 47 degrees. So I more than sufficiently met my phase margin spec. My gain margin is 14.9. That's now how you can perform a phase lag controller design using Bode Plot strategies. We'll look at the phase lead, which is now moving to the right instead of moving to the left.